Okay, good morning, everyone. In today's lecture, we will introduce the RC circuits. Now, what does RC stand for? R stands for the resistance, and C stands for the capacitance. So far, we have seen only resistors in our circuit. Today, we will add capacitors to those components. So far, we have seen resistors, and today we will see capacitors, and in the future we will also introduce the inductors, which is the third component in our passive components. Now, we have seen that resistivity is a signature for every material. Every material has its own resistivity, which basically defines the ease of the charges flow into the material. Capacitance, on the other hand, is a geometry dependent quantity. So those capacitors are used as an energy storing devices. They store the electric energy in the electric field. So how does this happen? If I have a circuit that has a capacitor that is fully discharged, and then I connected this capacitor to my circuit, then there will be a current flowing from the voltage source here through the resistor charging the capacitor. In this case, I can write a KVL equation here, which basically this loop, the direction of this loop is entering the negative terminal for the electromotive force, and that's why I wrote it as positive. It's parallel to the current I, that's why I wrote it as minus IR, and then it is entering the positive terminal of the capacitor, and that's why I wrote it as minus Q over C, which is basically delta VC. Now, this capacitor, it's going to now charge starting from zero charges, which basically the status of this capacitor at the beginning, and then the charges start to increase. Now, since the charges are going to get accumulated in this capacitor, I can go back now to the definition of the current, and I can say that my current IT here equals to dq over dt. And as I have seen earlier, when I have a capacitor now being charged, where the capacitor has two electrodes, one of them is positive, negative, and the current is going to charge this capacitor, then I can say that this IT equals to dqc, the function of time, over dt. So this is very important. As we will see later on, when the capacitor discharge, it will be a bit different. But this is what's going to happen. This is the current for this capacitor that being charged. Now, substituting this current with dqc over dt and rearranging by moving the minus IR to the other side and dividing by R, I get this equation. Now, if I take the minus 1 RC outside and I give the RC, the variable here, tau, which basically tau defines the time constant, as we will discuss later on, and epsilon times C is the maximum charge stored in the capacitor. We know that Q is CV and epsilon is the voltage and C is the capacitance. So this is going to give me the maximum charge that will be stored in the capacitor because of the electromotive force that does exist in the circuit. So now if I rearrange this circuit such that I move dt to the right, I move QC minus epsilon C to the left, then my equation would look like this. dqc over qc minus q max equals to minus dt over tau. Now, taking the integration on both sides will end up with this form of function. So I have now an exponential function for the for the charge that describe the charging performance of the capacitor. It's Q maximum times 1 minus e to the power minus t over tau. This is for the charge. This describe the function of the capacitor being charged and is given by this response. So how do you find this response? At t equals 0 for the exponential function, we know when t equals 0, I have e0 equals to 1. When t equals to infinity, I have e minus infinity equals to 0. So if I take the t equals 0 here, then I get QC 0 because now this one becomes 1. 1 minus 1 is 0. If I substitute e minus t over tau with the moment of t equals to infinity, then I have e to the power minus infinity, which is 0, and the answer would be q max, which is this value. So this is the exponential function for the charge, for the capacitor being charged. Now, if you want to derive this, you need to take the derivative. It is equal to dqct over dt. So derive it with respect to the time. It will give you this function where I naught here is the I maximum as well, which is the point when this which is closed right at that moment I get maximum current, and then it start to decrease also exponentially. And the voltage is Vt is the same function as the charge, however with different limits. Why? Because Vt equals to Qct divided by C. So the ratio here is the C, which basically is going to result into the same shape of this. However, here it will be Vmax instead of Qmax. There are two important points that you need to understand very well when it comes to the capacitor performance in the circuit. Let's assume we have this capacitor that does exist in this circuit, and this capacitor has zero charges in it when the switch was open. So it had no charges. And then at t equals 0, I close the switch. So how does this capacitor behave? Right at the moment when I close the switch, when the capacitor had zero charges in it, right at this moment, only that moment, I can replace the capacitor with a piece of wire. So right at the moment where I right at the moment where I close the switch at t equals 0, right at this moment, I will have a current flowing, and this capacitor now can be replaced by a piece of wire. Again, this is only at t equal 0, right when the switch closes. Only at this moment, I can replace now this capacitor with a piece of wire, and now I can calculate the current, and in this case the current would be I equals 2 epsilon divided by R. And if you recall, this was the I maximum for the current for the capacitor. So right at this moment, the current going through the capacitor, charging the capacitor right at this moment is the maximum current. And then once this capacitor starts to accumulate charges in it, then the potential difference between the capacitor and the electromotive force will start to decrease. So what we need to understand is right at the moment when I close the switch, and the capacitor has zero charges in it, you can replace the capacitor with a piece of wire. The piece of wire here means that this delta VC equals to zero, right? Any wire, the potential difference across that wire would be zero. So right at the moment, that's why I said this current is the maximum current, because if I take the KVL here, then I can say KVL epsilon, it would be positive, minus IR, right? Minus VC, if we're going to call it minus VC, equals to delta VC equals to zero. However, this one is zero, right at the t equals zero, which is when the switch closed. Then I is epsilon divided by R. And we said this would be the maximum current going through the capacitor only at this moment. Now this is when the capacitor was fully discharged, and then I put it in a circuit. Now what happens if this capacitor was left for a long time? So let's look at this case. I have a capacitor, and this capacitor had a switch here, and this switching is happening at t equals to zero. Now the switch is closed, and it was closed for a long time. How does the capacitor behave? The switch was closed at t equals zero, and it was closed for a long time. What's going to happen to the capacitor? How do I treat this capacitor? If the switch was closed for a long time, then now the capacitor is already fully charged, and then you can replace this capacitor with an open circuit. So how does this happen? So let's look at what's happening for this capacitor when I close the switch. Since I closed the switch till this switch has been closed for a long time. So now we know when this switch is for a long time, this capacitor is treated as an open circuit. Now let's look at what's happening to my capacitor. At the beginning, this capacitor was fully discharged. So we'll be looking now at those two moments. Once I close it and close it for a long time. Now this capacitor has zero charges in it when the switch was open. Right at the t equals zero, this is switch closed now. Then again, this capacitor, we said right at this moment will be replaced by a piece of wire. Where delta VC is zero. Then I can calculate the current, which is the maximum, would be the maximum current, which is epsilon divided by R. Now, let's look at the second moment. The second moment, this is not going to be 0 anymore. Now, charges will start to build up. We know that this is a capacitor C. Charges start to increase now. It's the charges in the capacitor was 0 before the switching, before the switch closed. Now the switch closed. I have maximum current flowing into this capacitor, filling up this capacitor. Now charges start to build up. Then the charge now will start to will increase, if you recall, exponentially, right? Why? Because charges are starting to build up now here. I know that V equals to Q divided by C. Charges start to increase, then the voltage drop across, you can call it delta VC, start to increase, right? This one start to increase, delta VC start to increase. Why? Because charges started to build up inside this capacitor, then delta VC start to increase. Is this delta VC is going to increase forever? No. There is a cap. What's that cap? I'll tell you what's this cap. As long as I have a potential difference across this resistor, then there is a current flowing. Why? Or I can say this, as long as the potential in this point is different than the potential in this point, I have a potential difference across the resistor, and then I have a current. Then what's going to happen is the following. The charges are building up in this capacitor. It will build up, and the delta VC will start to increase. The delta VC will keep increasing, which means that the delta VR will start now to decrease. The potential difference, because delta VC is increasing, then the difference between this potential at this point and the potential at this point will start to shrink, will decrease till the potential here becomes the same as the potential here, and then the current at this moment will stop and the charges will stop flowing. So the charge, and this is going to happen when the capacitor reaches the maximum charge. Once the potential at this point becomes the same as this point, which means that the potential difference across the resistor becomes 0, then there will be no more charges flowing to the capacitor, and at this moment the capacitor has reached its maximum charge. Now, leaving it for a long time means no current flowing, and if you have no current flowing, you can now treat this capacitor as if it is an open circuit, because when I have an open circuit, I don't have a current flowing into the circuit. So once I reach this moment where current in the circuit becomes 0, then I can now treat this capacitor as if it's an open circuit. So this is the definition of leaving it for a long time. So the switch is closed, and now it's closed for a long time. This means this current now is going to reach the zero level. And now, since it's zero, there's no current going into this capacitor. I can remove now this capacitor, and I can treat this capacitor as an open circuit. So it will be like this, only an open circuit. Then you can calculate delta VC when it's closed for a long time. So here in summary, when we have the switch closing at t equals 0, I can replace the capacitor with a piece of wire, which means the delta VC across this wire is 0. And I have now the maximum potential difference across R. So if you look at this one as a piece of wire here, as if there is a wire, you will see, and this one is closed, you can see that the epsilon is across the R and the epsilon now became in parallel, and that's why I have the maximum voltage now happening across the resistor R. For t goes to infinity, which basically means after a long time, so you did close the switch, and then you left it closed for a long time, which means t going to infinity. Now, guess what's going to happen? The capacitor would have reached the maximum, which is the voltage of the electromotive force, and that's why the voltage across the capacitor would be the same as the voltage across the battery or your source, and there will be no current going into the resistor, and that's why I said here delta VR across the resistor would be 0. So now the capacitor, when it's for a long time, you can now replace this capacitor with an open circuit, no capacitor, open circuit, and then you can calculate the voltage across those two electrodes. And here would be the current here would be 0. And as you can see, the electromotive force will show up right across the capacitor. The capacitor here will have the whole voltage of the battery across it. Why? Because there is no current going into this resistor, and this potential here now will show up here, and this potential is the same as this potential. That's why delta VC, when it's closed and for a long time, will equal to epsilon. Now, after we explained what's happening for the capacitor from the first moment when we close the switch till we left the switch closed for a long time, we can come now and do this question. Now, in this question, it reads the following: consider the circuit below. Switch is closed at t equals 0. What is the current through the capacitor C long after the switch is closed? So here, when we see the word long, means t is going to infinity. Now the switch here is closed, so I can redraw my circuit here, and the capacitor. So switch is closed. I have the battery here, 2 ohm. Since it's closed and for a long time, then I can replace now this capacitor with an open circuit, and then calculate delta VC. Let's call this one delta VC or VC, 6 volt. So guess how much the voltage across the capacitor would be here. Here, I replace this capacitor with an open circuit. I'm treating the capacitor as an open circuit. This doesn't mean that I have physically removed it, but I'm treating this capacitor because it's long time after the switch closed, long time after the switch is closed, then I'm treating this capacitor as an open circuit, and now I can calculate the voltage across this capacitor. The word open circuit means I have 0 current going into my circuit. This is the definition of open circuit. I have 0 current. So now I can calculate the delta VC. If you want to apply KVL, you can do that. KVL, it's going to give you here 6 minus 2I, and don't forget that I equals to 0, minus delta VC equals to 0, which means delta VC equals to 6 volt. And don't forget that the current here is 0 ampere because the switch is closed. So here we need to calculate the current, and the answer is A. But we also understood that the capacitor is treated as an open circuit, and then the potential difference across this capacitor would be the same as the voltage source here, which is 6 volt. Now let's look at the second case where the capacitor is discharging now. So the capacitor was already charged, and now it is discharging. How is this capacitor going to behave? Again, if you write KVL, then you have minus here, you have positive delta VC, you have minus IR equals to 0. And this delta VC is QC divided by C, minus IR. And remember, we said that the definition of the current is dq over dt. In the previous case, we said dq over dt equals to dqc over dt because the capacitor was charged. The direction of the current is charging the capacitor. Here, the capacitor is being discharged. The capacitor is discharging, so the current is going in the opposite direction, and that's why we said now I should be substituted with minus dqc over dt. So if I am to substitute I with minus dqc over dt, rearranging the equation, this is the equation that I get. Again, then here rearranging such that the dq over q on one side and the dt on the other side, and taking the integral for both sides while t is integrating from 0 to t. Now q is integrating from q maximum, because now it is discharging from q maximum to qt. So taking the integration, substituting, and rearranging, we get this expression, which is also an exponential function. Which means now that the capacitor is going to discharge with this function from whatever charge it was at till the charge becomes 0 at infinity. Now, tau, we said, is called the time constant, and it's now important to know that after 1 tau, so tau is a time constant, and this is my function that describes the charge versus time. Now assume I want to calculate the charge after 1 tau only 1 tau, which basically here substituting t with tau, this is going to result into q equals to q max e minus 1. So this represents the tau, the value after tau. Now always keep in mind that this is going to give you a value that is shifted 0.37 or 37% away from the final destination. So if my final destination here is going towards 0, then a shift of 37% means this point, which is 0.37% Q max. Now, if I go back to just to jump back to the capacitor, that is being charged. At tau here, again, this one is 37% from the final destination. So this is the final destination. It is 37% shifted, which means here is the Q at this would be 63%, 0.63 Q max. So it is always 37% away from the final destination. My final destination here is Q max, so it is 0.63% Q max. My final destination here is 0, and that's why it is positive 0.37% of the Q max. Okay, so again, this is the function for the capacitor being discharged. Now look at this capacitor here. This capacitor, if it's being discharging for a long time, it will definitely reach a zero charge. So let's look at this example. Here in this example, the switch was closed at t equals 0. Right at the moment when the switch was closed, right at the moment when the switch was closed, let me draw the circuit here. So this is my circuit. I have the capacitor here. I have R2 here. I have R3, C, R1, battery, then I have the switch. Now, when the switch closes here at t equals 0, we said what's going to happen to the capacitor. Right at this moment, when the switch closes, right at this moment, I can replace this capacitor with a piece of wire. What does this mean? This means my delta VC here would be 0 because this is a wire. So what can I do here? Now I can calculate the current at t equals 0. This is the capacitor as a piece of wire only at this moment. Then I can calculate, do exactly the same of what I have done before, and Kirchhoff's laws and Ohm's laws, apply Kirchhoff's laws and Ohm's laws. I can calculate the current and in this branch, and guess what? This would be the maximum current going into the capacitor only at this moment. I can calculate the current in this branch. I can calculate the potential difference across R2, across R3, whatever I want. Then, long time after the switch is closed. Now look what's going to happen now. Now, long time after the switch is closed, we need to draw the equivalent circuit. So let's draw the equivalent circuit after the switch is closed for a long time. After the switch is closed for a long time, this is going to look like an open circuit, right? This is going to look like an open circuit. And guess how much the current would be here? Would be 0. Current here would be 0, right? So this is delta VC. So this is the equivalent circuit after the switch has been closed for a long time. Now, this is A, item 3B, currents through the resistors. We need to calculate the currents through the resistors. We said that the current in here, let me call this one I2, would be 0. So you can completely eliminate this branch here, and now the current in R1 would be the same as the current in R3. So let me call this one I1, and in this case I1 would be epsilon divided by R1 plus R3. Now, how much is delta VC? This is another important point. How much is the voltage drop across the capacitor when the switch is closed for a long time? Now the potential here, because the current here is zero in this R2, then the potential here will show up here. So the voltage delta VC across the capacitor will be exactly the same as the voltage across R3. Delta VC will be the same as the potential difference or the voltage drop across R3. Why? Because there is no current going in here, zero. If there is no current going in here, then the potential difference between this point and this junction, and this junction is zero, which means the potential here is the same as the potential here. Which means that now the potential difference across the capacitor is the same as the potential difference across the R3. Item 4, the switch is closed for a long time, then opened again. So the switch was closed for a long time and then opened again. Which diagram would be equivalent just after the switch is open again? So this is very important. The switch was closed for a long time, and now the switch is open again. So let's see what's going to happen. Switch was closed for a long time. And then the switch opened again. But when the switch was closed for a long time, now how much the voltage across delta, the capacitor was the same as the voltage across R3, which means delta VC was I1 times R3. So there is a value. There is a value that I managed to calculate from my circuit when this one was the current going into this resistors R1 and R3, right? Now, I got this value. I have delta VC across the capacitor, and now the switch was opened again. Now, guess what's going to happen to the capacitor? Now, the capacitor will be replaced by a battery, and only for that moment. And this battery is delta VC. So now I can redraw this circuit. I can redraw this circuit. Now, since the switch is open, this whole part of the circuit is going to be useless. Why? Because now the circuit is broken. So I need only to focus on here. So look, this is what's going to happen. The capacitor will be replaced by a battery. And this battery now is delta VC. I have a resistor here. And I have a resistor here. R2 and R3. This is now a new circuit. This whole part, because now the switch is open, so the circuit is broken. There is no current going here. So now I can remove this part, and I replaced my capacitor that was charged with delta VC equals to I1 R3. I replaced it with a battery, and now this capacitor will be responsible for providing the current in my circuit. So this is going to be the circuit diagram after I replace the capacitor with a battery. I replaced it with a battery because it was charged, already charged, and then when I open the switch, it will act as a battery with a value of delta VC only at this moment. Now, what's going to happen when the switch stays open for a long time? The capacitor will discharge all the charges in it, and it will reach to a zero charge. So and then you can say that it became an open circuit because there will be no current flowing into the circuit anymore. Then you can replace this capacitor with an open circuit, and after a long time, my circuit is going to look like this. And now the voltage across the capacitor here would be zero. Okay? The voltage here, after a long time of being open, the current would be zero. The current here, I is delta VC divided by R2 plus R3.